Okay, so here's another inclined plane problem. So here's the ground, and here's an inclined plane. And this angle, we've inclined it at theta. Let's use 30 degrees. So then keep in mind here, sine of 30 degrees is equal to 1/2. So 0.5. That will come in handy to do the problem. And we're going to have an object sitting on here, right? And if we release the object from rest, it'll start to accelerate down the incline. And let's say that for this problem, there's no friction. Okay, so then how do we keep this thing, if we want it to stay still, how do we keep it from sliding down the incline? Easy, we use a string, all right? So let's just finish the ramp here. Like that, and we have some little contraption up here, and then let's tie a string to it. Bloop, and so there's a string. And that string is holding this block, and it's keeping it from accelerating down the incline. Let's give the block some mass too while we're at it here. Let's say it's 5 kilograms. Okay. And so, first question, what is the tension in the string? The string is keeping it from slipping. So there's a force exerted by the string. And that force, the force in the string or cable, is called tension. So to solve this problem, I'm going to draw this thing called a free body diagram. So all the forces acting on the block. So those forces are going to be, well, there's the weight of the block, which acts straight down, and that is equal to mg. So right off the bat here, we can figure out how large that is. M is 5, and the value of little g is about 10 meters per second squared. 5 times 10 is 50. And the kilogram times a meter per second squared is also called a newton. So the weight of this block is 50 newtons. Then the other forces acting on this, well, there's no friction, so nothing to draw there, but there is the force of the ramp acting perpendicular to the surface of the ramp at an angle. That's the force that keeps the block from falling through the ramp. That's called a normal force. N. And finally, the force that keeps it from sliding downhill is the string, and that force is a tension force, T. So then the key to doing these inclined plane problems is to rewrite what mg is in terms of the components of mg acting down the incline and perpendicular to the incline. And we've talked about one in the previous video. Part of the force of gravity on this object wants it to slide down the hill. So there's a component of gravity acting downhill. And that component we can draw right here. And that component is mg sine theta. The other part of gravity that's acting perpendicular to the incline and keeping it pushed against this thing, it points this way. And that component of gravity is equal to the force of gravity times cosine of the angle. So times cosine theta. So once you have those two components of gravity, for this type of problem, you don't really need to worry about gravity anymore. It's just those components of gravity. And then the other thing to keep in mind here is our coordinate system. Our coordinate system is now inclined like this. So here's X and Y. And you could call this direction positive if you want to. You could call this direction positive. In this problem, what are we going to do? We're going to call the upward direction positive. All right. So this way is positive. And we're going to write down Newton's second law, which says net force is equal to ma. But in this problem, the block is being held up by a string. It's not going anywhere. It's not moving. It's not speeding up. It's not slowing down. It's not changing the direction it was moving, if it was moving. It's sitting there still. So what does that tell you about this guy? Yeah, it's 0. And anything times 0 is still 0. This just tells you the net force acting on the object is, guess what? It's 0. Next, write the expression here for net force. In this case, it's going to be between these two forces. The net force in the direction of the incline here, well, one of those forces is mg sine theta. The other force is tension. So let's write down the net force in terms of those two. They're pointing in opposite directions, so you subtract them. So T minus mg sine theta is 0. We could actually write in here right now what mg sine theta is. So it's going to be T minus, m is 5 kilograms. G is 10 meters per second squared, and sine of 30 is 0.5. Oh my, all these numbers. So T minus, so 5 times 10 is 50. And 50 times 0.5 is 25. So T minus 25 newtons is 0. So that means that the tension in that string, it's 25 newtons. All right. So yeah, the tension is 25 newtons. And there you go. Problem done.